In this video we're going to look at the equilibrium law, or more specifically the equilibrium constant, Kc. Kc is a constant that gives us a relationship between the amount of products we have, i.e. the concentration of products and concentration of reactants in a system that's in equilibrium. So we're going to look at a generic system first, where we have A and B reacting to produce C and D, and the small letters in front are just the number of moles of each species according to the balance equation, i.e. the stoichiometry of the reaction. Kc is equal to the concentration of the product to the power of its number of moles times the concentration of the other product to its number of moles according to the balance equation, divided by concentration of A to the power of A times B to the power of B. So we basically take the concentration of each species in the reaction and put it to the power of the number of moles of that species involved in the reaction according to the balanced equation. And that's how we work out Kc. Now Kc gives us a lot of information about the equilibrium. We're used to saying from our previous videos, we're used to talking about a position of equilibrium lying over to the right or to the left. Now we can see that if we've got quite a high Kc, that means we've got probably quite a large amount of products there, so our position of equilibrium lies over to the right. And if we've got a low Kc, then our position of equilibrium probably lies to the left. So that's going to be a low Kc, and this one's going to be a high Kc. Now in terms of the leaving cert, we usually only use Kc to work out concentrations of species or to work out a Kc itself. We're not going to go into how Kc changes. We know that Kc changes with temperature. That's linked to Gibbs free energy, but we're not going to talk about that because it's not on the leaving cert course. So I'm going to go through a calculation now, again just using generic reactants and products, and we're going to try and work out a value for Kc for a reaction. So if I have a reaction like this, A plus B going to C. Now quite often you're not given all of the information, okay? You're going to be told a certain concentration of the reactants potentially, and you're going to be told that at equilibrium there's a certain concentration of products. Or you might be told the number of moles, for example, of reactants. So in this question, I'm told the number of moles of A is 0.5. So we're going to look up the number of moles. That's 0.5. And then at the start, the number of moles of B is 0.3. And at the very start of the reaction, nothing has happened yet, so therefore we've got 0 moles of C. Now in this question, I'm told that at equilibrium, 0.1 moles of C has formed. And I'm told that there's a volume of 10 decimeters cubed, which is 10 litres. Okay, so at equilibrium, I know that there's 0.1 moles of this. Okay, if there's 0.1 moles of C, well, as A and C react in a one-to-one fashion, that means if there was 1.1 mole of C formed, at equilibrium there must be 0.5 minus 0.1 mole of A formed. And likewise, there must be 0.3 minus 0.1 moles of B. So that's just going to equal 0.4 moles of A, 0.2 moles of B, and 0.1 mole of C at equilibrium. Now, so the volume is 10 decimeters. Well, if the moles is 0.4 and the volume is 10, therefore the concentration of this is going to be 0.4 divided by 10, concentration of this is going to be 0.2 divided by 10, and the concentration of this is 0.1 divided by 10. So how do I work out Kc? Kc is equal to 0.01, which is this figure here, divided by 0.04 times 0.02, which are these two figures here. And that gives me a result of 12.5. Now we need to work out the units. That's going to change for every type of reaction. It's going to change because the number of units at the top might differ in every reaction to those that are on the bottom. Okay, so just to explain that again, we know that the concentration here is in mole per dm cubed, concentration of here is mole per dm cubed, and the concentration here is mole dm cubed. So what I know from this is that we've got 1 mole of dm cubed will cancel with 1, and so the units are going to end up being 1 over mole per dm cubed, which is equal to mole to the minus 1 to dm3. So it's 12.5. So we're going to look at a specific reaction here, hydrogen and iodine reacting to form hydrogen iodide. And I'm asked to work out all three equilibrium concentrations. So at the start I had 0.2 here, I have 0.2 here. I obviously have nothing at this at the start, and Kc is equal to 64. So for this one, we're going to introduce an unknown, X. So we've lost a certain amount of hydrogen, we've lost a certain amount of iodine, and if we've lost X amount of hydrogen, well, for every X hydrogen that reacts, we form 2 moles of hydrogen iodide, so this is going to be plus 2X. So then at equilibrium, we must have 0.2 minus X, 0.2 minus X, and we must have 2X of this. So to solve this, we're going to end up with an equation in X. We know that Kc is equal to 64, so 64 is going to be equal to our equilibrium constant. Well, that's going to be 2x all to the power of 2, because we've got a 2 in front of that, all divided by 0.2 minus x times 0.2 minus x. So we're left with a convenient situation here where we just take the square root of both sides. We could multiply everything out and just solve the quadratic equation by plugging into the minus b formula, but what we're going to do here is take the square root of both sides because it's convenient. We know that this square root of the left hand side is just 8, and the square root of the right hand side, if I take everything, it's just going to be 2x all over 0.2 minus x. And if I expand out both sides, I can solve for x, and x turns out to be 0.16 mole per decimeter cubed, because these values here were concentrations.